Uh-huh. Shh. Alvin, could you close the door for us so we don't get outside noise? Sorry about that, Adriana. So we have 4 gas molecules on the left, 2 gas molecules on the right. So entropy favors reactants. We have our heat term is over here, so this is my lower potential energy side. So enthalpy also favors the reactants, so it should not proceed. That's okay, no problems. Anything else? Okay, in that case, let us go to our little AP extras, and we're going to go to 2.5b, which is on page 6. I am recording. I did it today. I know, I'm so proud of myself. Thank you for asking, though. I appreciate it. Okay, for gas phase equilibria, and I cannot talk over you today, otherwise I'm going to cough all day, so. It is sometimes easier to use partial pressures instead of molarities. Therefore, we can use partial pressures in our KEQ expression rather than concentrations. Yes? So, however, and then if we use partial pressures, we call it KP. Yes. What's a partial pressure? Okay. Go back and review your gas stuff. I don't know if you did the gas stuff. Partial pressure is the pressure, the proportion of a pressure due to one particular gas in a mixture of gases, okay? Now, the nice thing is, do you guys remember what mole fraction is? Okay, definitely, if I ever do those morning sessions again with another group, I'm going to make them mandatory rather than optional, because you should know mole fraction. Everyone should be like, oh, mole fraction. Oh, yeah. I've heard that word before at the very least. Have you heard the word before? You know what a mole is, you know what a fraction is, and in fact, that is all there is to it, okay? It is represented by the letter X. I usually put these things on it just to make it look like a fancy X, okay? And if I write X of A, that's the mole fraction of gas A. So let's just say for example, a mixture of gases contains 1 mole of A and 4 moles of B. What is the mole fraction of A? Yes. Yes, and you can write that as either 1/5 or you can write it as 0.2. Okay? Is good? All right, that's what a mole fraction is. I feel like I should have done this on a completely separate piece of paper, but there we are. Let's see, where can I fit in? Oh, look, here we go. Partial pressure of A partial pressure of gas A is equal to, what does that thing stand for? Mole fraction of A times the total pressure, yes? Due to all gases. Does it make sense that if 1/5 of your particles are A, they will contribute to 1/5 of the pressure? Yeah? Okay, that's all that's really saying. Okay? That's it. Right? So you don't need like fancy formulas. You can just be like, 1/5 of the gas is A, therefore 1/5 of the pressure is caused by A. So if I had a pressure of 100 atmospheres total, how much would be due to gas A? 1/5 of that. What's 1/5 of 100? 20. So 20 atmospheres would be due to gas A. And if we had 4 moles of gas B, if 80% was, it would be 80 atmospheres would be due to gas B. Okay? So that's all there is to that. It's actually really straightforward. So no worries if you didn't know it or you forgot it, that's all okay. And we have our mole fraction of A. We've just got the formula here. So we'll be playing around with these values in the context of finding equilibrium constants. So Kp expressions, just like Kc expressions or Keq expressions, what's the difference between Kc and Keq? They're the same thing. Nothing is different. What's the difference between them? Nothing. Kc is Keq. Okay? Kp is simply a Keq done in pressures. Kc is Keq done in concentrations. And if we just use Keq, we assume we're doing a Kc, a concentration equilibrium constant. So Kp, do not include values for solids or liquids. Why? They don't have pressures. Well, I mean, liquids have pressures, but they can't change in pressure. Just like technically you could say a liquid has a concentration. There's a certain number of moles per liter, but it's going to be constant, right? You cannot change the moles per liter of water if you have water, right? It's like, there it is. The only reason I say water can have pressure is if you're underneath the water, you can feel the pressure on you. Yes? Okay. Yeah. Yeah. Yes. Okay. In the what block? Of course it's block 2. Why would anything ever be in anything other than block 2? Fuck me. Sorry. Oh, that's going to be on the recording. That's fantastic. Okay. Edit. But it's in the middle. It's too much trouble. I'm just going to assume that nobody's going to watch my videos other than you guys. And you already heard me say the bad word, and you're grown-ups pretty much almost, so you're okay with it. All right. We can do the quiz Friday. I don't care. It's fine. Yeah? Yeah, Friday's okay? You'll be fine. Friday is your quiz. Okay, and we need to stop having things during block 2. Yes. It doesn't matter. Most of them are grade 12, so just don't worry about it. We're just moving it to Friday. Your quiz is moved to Friday. Okay? Yes. I don't know, but they could call you out at any point during the block. Do you know what I mean? Right? So, yeah. All right. That's just super. Super. Okay. At any rate, the KP expression for, but that's okay because I haven't marked your other quizzes yet, so that'll give me a little more time to do those before I get the other one. It's not as ideal because I would have liked to have gotten those back to you before the weekend, but you know, that's okay. Write the KP expression for, oh look, we have a solid, we have a gas, we have a solid, and we have a gas, so it's just the gas over the gas. That's it. Easy? Yeah? Right? We got our H2O to the 4th. Got our H2 to the 4th. Is good? Okay. Tasks you may be called upon to do using KP. Calculate KP given the partial pressures. Pretty easy, yes? Calculate KP given some of the partial pressures. If you know the partial pressure of A and the partial pressure of B and the total pressure, and you're asked to calculate the partial pressure of C, could you do it? Yes, right? Because P of A plus P of B plus ... equals P total. Yes? So as long as you know like 2 of the 3 or 3 of the 4 or whatever, you can do that. Calculate Kp given moles of each gas at equilibrium. You would also have to, I believe, be given a total pressure, okay? Yeah. Right, so you could be given moles of each, and then you can calculate the mole fraction. Calculating the total pressure from Kp and moles of gas at equilibrium. Yeah? We're going to look at how to do all of these. And finally, this is something new, percent dissociation, but we'll look at that in context, okay? It's just what percent has actually come apart, what percent is staying together, etc. Okay? Okay. I didn't even think it was worthwhile you writing this down, right? Because at equilibrium, we are found that the partial pressures are bam, bam, bam. Could you solve for Kp? Yes. Easy? Because you just write your expression, which is just like Kc, except for you use P. Okay? Now, for partial pressure, you can either write P NH3, but you'll also see it written as PP NH3. Okay, either of those are correct for partial pressure of NH3. Is good? Okay. All right. Example 2. At equilibrium, the total pressure. Why don't you cover up the answer for yourself and see if you could solve it? Get yourself a blank piece of paper, or just cover it up with your answer key or any old book or anything and see if you can solve that. There's lots of blank paper at the back if you want to cover it up with that and write your answer on it. We are on example 2. Example 2. If you want to do example 3, you can do example 3. Did you guys get point 2? Yay! You could try example 3. Once again, cover it up. What's up? Uh-huh. Which formula? Oh, but you don't have mole fractions. Well, I guess you could say my partial pressure of H2 is 0.016 over, or whoops, 0.013 over 0.016. Is that what you did? Oh, you can do this, but you're just going to end up doing 3 steps what you could do in 1 step. Yes? So you could do this because mole fraction is going to be either the moles over the moles. It's also going to be the pressure over the total pressure. because moles and pressure are directly related. Yes? So you could find mole fraction of H2, you could then find the other mole fraction by like subtracting from 1. Yes? And then you could calculate it, but it's much easier to use P total equals pressure of A plus pressure of B, and then solve for the other one. Yeah? Okay. Yes? Shouldn't, because they're both multiplication by the same number. Oh. So KP actually does depend on the unit. So technically, sometimes KPs are given with units. But if you don't want to give a unit, you don't have to give a unit. Yes, the value might be different in terms of, but the ratio, but it'll remain constant. You have any idea what I'm saying? Because I feel like I'm just rambling now. Yeah? We're okay? All right. Don't get too worried about KP. It's usually in the context of AP. It's really easy, right? It's like, oh, here's some partial pressures. Throw them into the formula. Okay? So don't get too wound about it. Have you done example 3? Who's done example 3? Not yet. Do example 3. Get yourself some paper, give it a try. And when you're done, check your answer. There is paper back there. Just go get the paper or get your own paper. Half of the reason for doing this is just to remind you about partial pressures and mole fractions, to be honest. Do you need a book, Arwen? Just because you're kind of squinting up at the screen. You're good? Okay, just making sure. Okay, my friends, have we managed it or are we still working? I just wanted to show you an alternate way of doing it. Like what I've done is I've, like up here, I'm like, okay, we're solving for the mole fraction, and then we're finding the partial pressure. You don't actually have to write this step. You could just go right to here. Okay, that's perfectly good. Yes? And in fact, you don't even need to write this step separately if you don't want to. You could go straight to plugging in. You could go from here and then plug in the values as mole fractions. I feel like I might get confused if I did that because there's a lot of ninths floating around and I have a tendency to like screw up which one is which if I don't label them carefully. But if you're confident with doing that, you can totally just go straight to there if you want. Is good? Okay, let's do something a little more complicated here. Do you think you could do question number 4? It's trickier. Do you want to try? Why don't you try? See if you can think your way through it. Call me over if you get stuck. Hello. Yeah, yeah. Uh-huh. From like kilopascals, You can, you can give a unit for KP if you want to. Oh. But just like KC, you don't have to. It doesn't matter. As long as you keep working in the same version of pressure units, yes? So you don't want to like switch to atmosphere altogether, right? I could, but I'd have to. You'd have to, yeah, yeah. Exactly. Yeah. I'm gonna love it. I told you yesterday I was going to. Can you please write a small in the group chat? She asked me this. No, he said how long will the meeting happen? No. Anyone have any questions? The only reason this atmosphere is here is for you to know what unit to put your pressure in at the end, okay? not have any idea how to do this question, what could I probably start by doing? Mole fraction, yes? Because I'm like, oh look, I got moles, I can make a fraction, I know I need to do that with pressures. Sure, let's see if that takes me somewhere useful. Okay? And you could get part marks for showing that worked, even if you didn't know how to do that, right? Anyone made that before? The answer as written is wrong because apparently I can't write things properly. So the trick here is that you want to express your pressure of each gas in terms of P total. And the reason that you want to do that is that then you only have one variable instead of 5 variables or whatever the heck, 3 variables. Yes? So you know that the pressure of CO2 is the mole fraction of CO2 times the total pressure. You can calculate the mole fraction in a separate step if you want to. Okay, it doesn't have to happen all in one line. So we've calculated our total moles of gas. We know that there are 2 moles of CO2 per 7 moles of total gas. And so you get this fractional, this number here. Is good. And the only problem is apparently I can't read the number 4 because I wrote 6 instead of 4, which of course is going to mean that that number is going to be wrong. Okay. And so our final answer 0.2857, 0.1429, 714 false. Yeah, is that looking better? Is good? Okay, cool, cool, cool. Do I think you're going to get a question like this? I don't think so. But, you know, it proves to you that you can go out and solve equations just by knowing how to do some math, and it reminds you what a mole fraction is and all that good stuff. Percent dissociation is something I have seen on AP exams, not necessarily in this context, but this will at least let you know what they mean by it. It's pretty straightforward what they mean by it. What do you think? If something is 20% dissociated, what does that mean? It means 20% of it has split apart, yes? So if you have N2O4, it can dissociate into NO2 and NO2, yes? And if it is 20% dissociated, you'll notice here that we aren't given any moles, yes, in this question. It is usually easiest if you are not given moles to assume you start with 1 mole because it's easy to find a percent of 1. 20% of 1 is 0.2. So you're like, oh, okay. So I know that out of my 1 mole, 0.2 moles was dissociated. 0.2 of it came apart. Yes? And once you've got that, this is just a race table here, you know that you end up with 2 NO2s for every 1 N2O4 that comes apart. So instead of 0.2, it's going to be what happened? Did we all just stop paying attention? Instead of being 0.2, it's going to be 0.4 because it's twice as much. You're starting with nothing here. Just do the math. You get 0.8, 0.4. And now you're finding total moles of gas. You're finding a mole fraction and a mole fraction. From there, you can find your partial pressures, and then you just plug it into your equation, and Bob's your uncle. Is good? Okay, cool. Where did I put? Oops, there. 2.6a, page 11. Nothing new at the top of the page. I'm going to stop talking for a second, and I'm just going to circle things and point at it, and you're going to do it. what's up with my front row today? Front row, turn around and talk to people behind you. I got one person in my front row turning around and talking to people behind them. Turn around and talk to the people behind you, front row, since you're not participating in my vote and you're making me talk. All right, what do we think? Number 1 is plus, 2 is minus. Yay. Okay, wouldn't it be nice if we could actually put some numbers to delta S? Just like for enthalpy, there are tables of standard entropy values. They can be found in most textbooks in the appendix section. I have provided one for you on the next page. It's not beautiful because I don't know why I could not get a good image, but that's okay. Do you remember this formula here? What does this little doodad mean? The sum of. Do you have any problem remembering that it's products first and then reactants second? We're good with that? And it's going to be the same for delta S. Look, same formula. And guess what? It is also in your, this formula I think is in your data table. Let's take a look. Yep. You don't even need to remember it. It's in the data table. Okay? Isn't that nice? So, now there was one thing that you might remember from back in the day. Do you guys remember what is delta H, standard enthalpy of formation of an element at standard state? Zero, okay? This is not true of entropy. So if you think of entropy as randomness, the amount of disorder, etc. Is it possible for anything that's not at absolute zero to have zero randomness? No, anytime there's any kind of motion whatsoever, you have some degree of randomness, yes? So it is impossible to get to zero entropy unless you are at absolute zero. Okay, so you guys can try this question here using the S values from the next page. Yes. Why is the unit of enthalpy which? So enthalpy is kilojoules per mole. For whatever reason, entropy is usually given in joules per mole Kelvin. Now, what is your question around that? Because I didn't really get Q equals MCAT? Yeah. Oh, it is similar. Yeah. There's probably a relation between the two. I just don't know what it is. But it would make some sort of sense because when we start looking at Gibbs free energy, it's got a minus T delta S per minute. So that sort of reminds me of what I want. Beyond me. Yeah. Am I? Oh, I might not be. Oh, it's a gas. Let's see. I bet I did not. I bet I just grabbed the first one I saw. The good thing is when you get this, yeah, 188.7 it should be. The good news is that on the AP exam, they're not going to give you a table. You're just going to be given values in the question. Yes. I don't know. I'm just not gonna, I'm not even gonna think about that. Sorry. Because that doesn't make sense to me, but you know, whatever. There's many things in this world that don't make sense to me, so I'm just gonna go with it. What did you guys get as a final answer? Sorry, what? 180 kilojoules or joules? Just joules? And how many decimal places should you have? How many decimal places should you have? This is all addition, right? Even when I multiply by 2, it's because I'm adding it up twice. Yes? So I've got a 0.1, I got a 0.1, I got a 0.1, I got a 0.1. So my answer should go to 1 decimal place. What's my decimal place? Okay, I got to do it myself because nobody's answering me. Fine. Okay, obviously I'm doing something wrong because I got 153.7. And I forgot to put my units out here. Okay, I'm gonna try it again. 28.3 plus 3 times 188.7 equals minus 50.9 minus 3 times 130.6 equals. Oh my God, I'm getting a totally different number again. What number are you guys getting? Okay, I got 125.683, which is obviously incorrect. So I've pushed something wrong. 2 times 28.3 equals plus 3 times 188.7 equals minus 50.9 equals minus 3 times 130.6 equals, it is 180. And it should be 180.0. Is good? Okay, easy. So why is delta S here large? Let's see what we mean by large instead of close to 0. Why do we get a largish delta S here? Explain to your partner. I feel like we skipped over something back in the regular equilibrium section. Can I go look? Yeah, I'm gonna go look for a second. Oh, yeah. Yeah. Where is it? Oh, it's not here. Where is it then? Well, maybe it's in here. Oh, yeah, it is. Okay, never mind. Anyone know? We have 3 moles of gas over here. We have 3 moles of gas over here. So why is delta S large instead of close to 0? Yes? That doesn't make much difference. I love that answer, but it's not true. Yes? No. Alvin? Maybe because molecule is polar? It does have to do with what the molecule is. No. We're going to take a look at this, okay? More complex molecules, and you haven't learned this yet, so I wouldn't expect you to know it. More complex molecules have more entropy than less complex molecules. So H2 is less complex than H2O. Is good? Okay, let's take a look at why. So do you remember all the different ways that molecules can move? What can molecules do? They can vibrate, right? They can rotate and they can translate. Now, everybody can rotate and translate, that's fine. But if we look at H2O, okay, here's the H, here's the O, here's the O. What kinds of vibrations can you have? Do you remember? We can have, and you're going to do it with me, symmetrical stretching. Symmetrical stretching. Let's try asymmetrical stretching. Okay. Let's try. Ooh. Yes. So we can have bending, we can have asymmetric stretching, right? We can have symmetric stretching and we can have bending. Now, I would like you to try just H2, there's no O, just H2. What can you do? Can you do anything else? Can you do asymmetric stretching? No. Can you do bending? No. That's rotating. Okay? So basically, if you have H2, the only thing you can do is symmetric stretching. You cannot asymmetrically stretch. That's not a thing. That's just the same thing as going like this, right? So we're going to take a little look at a video here. Where is it? Yeah? No. Let's see if this works. Oh, here we go. Yes? So these are called degrees of freedom. The more degrees of freedom you have, the more entropy you have. So water has these 3 degrees of freedom, plus the rotational and the translational. You're not going to have to count them up for AP. Okay, don't worry about that. Yes? Oh yeah, it does those things at the same time, right? But they count as 2 different motions, right? So that's basically the rationale behind why you get more degrees of more entropy with more complex molecules, is they have more degrees of freedom. Now, how often does this show up on AP? Not very often, but you should be able to talk in terms of degrees of freedom. I have seen them put that language forward in a chief reader's report. Okay, so what did I do with 10? There it is. Now, in relation to vibration, this has shown up one time for 1 mark on an AP exam since 2014. Woo! Vibration is caused by infrared radiation. If you think that is an important thing for you to stuff in your head, you can kind of remember it, because it's like, if you know Ohm's law, which I imagine a lot of you know Ohm's law. If you don't know Ohm's law, this will not help you. But Ohm's law is V equals IR, yes? V equals IR. Vibration is caused by infrared radiation. It helps me remember it. If you don't know Ohm's law, it won't help you. You would have to come up with something else. For me, I always remembered Ohm's law because it sounded kind of like a bird. Ver, I don't know. Yeah. My brain just makes weird connections, and then it thinks that's okay. It's like bird, Ohm's law, bird, verb, V equals IR. I don't know. Anyway. All right, so rotation. Let's take a look at the degrees of freedom for rotation for water. Water can go around the y-axis. Yes? Water can go around the, and I cannot do a complete rotation here because I'm not going to, okay? It could go around the x-axis. And water can go around, if I was willing to do a cartwheel, we could go around the z-axis, yes? Now, hydrogen only has 2 relevant rotations, right? If you have hydrogen, it can go, yes, or it can go on the y-axis, right? But spinning on the one axis, that's not considered a degree of freedom, because the molecule is essentially identical if it's spinning like this, right? If you've got an H here and an H here, nature can't tell the difference between whether it's here or here or here or here, as opposed to this or this. Is good? Okay. Again, you don't need to count those. You can just say water is more complex, therefore it has more degrees of freedom. Therefore, it has more entropy. So AP, like I said from the Chief Reader's Report, they seem to like the discussion of more degrees of freedom means more entropy. Okay, so I'm going to write that down. More degrees of freedom equals more entropy. Now, once again, one time for 1 mark on an AP exam between 2014 and now, like in the last 9 years. Rotation is caused by microwave radiation. And you know how I remember that one? What happens when you turn on the microwave? What happens inside the microwave? The thing rotates, yes? Oh, look, rotation is caused by microwaves. That's how I remember that. You are responsible for knowing that the more complex and asymmetrical a molecule, the more degrees of freedom, hence the more entropy. Let's take a look at this video here. I'm going to go grab it from, this is what, 2.6a? Sadly, I've not put the link in my OneNote. Or do we even have time? Yes, sure we have time. Sure we have time. Yeah, what the heck? Or maybe I should just give you your homework. Does that make more sense? Let's do that. Let's give you your homework, and we'll do that next day. In your AP booklet, pages 4 and 5, AP extras. Ooh. Because your quiz isn't until Friday, I'll give you some of this stuff now. Pages 4 and 5, and what else? Pages 9 and 10. And I think that should be enough. Yes? Don't do every single question if it's too much time. You'll notice that they all have an A and a B. You might just do the A's, right? Or something like that.